So when we take a look at the cellular elements that are in blood, we have red blood cells, white blood cells, and platelets. We spent the entire last lecture covering the structure and function relationship of red blood cells, including why they look the way they do. And white blood cells are going to be saved for immunology. Now we're going to cover the last one, which are platelets. Now platelets are actually kind of like dandruff, cell dandruff, so they're just particles really of a much larger cell called a megakaryocyte. So the word mega means large. So megakaryocyte. So these large cells, which are also made out of hematopoietic stem cells, so remember hematopoietic stem cells can make red blood cells, megakaryocytes, and any of the white blood cells, are going to shed platelets. Now platelets are not even true cells, they're just fragments of cells. As such, they have one of the lowest life expectancies. Whereas red blood cells have a life expectancy of 4 months, platelets have a life expectancy of like 7 days. Platelets are involved in clotting. And clotting, or the process of clotting and stopping blood from leaving a blood vessel, is called hemostasis. Not to be confused with homeostasis. That means something different. Hemostasis is the process of actually stopping blood from leaving a blood vessel. Keep the blood in the blood vessel. So if you have a rupture or a tear in a blood vessel, blood's going to leak out, right? So you make a clot to try to patch up that damage until you can rebuild the lining of the blood vessel. So hemostasis is the process of keeping the blood where it is, and of course a major part of that is making a clot. So we're going to talk about the clotting process here in a moment. Platelets are an intricate part of the clotting process. When platelets are made, they come in kind of this, what I'm going to draw it as is like an inactive form, like so. The inactive form is not sticky, so these are non-stick. Certain chemical signals, paracrines, will activate them and will turn them into a sticky form. And I always think those sticky forms look like the burrs that sometimes get caught in dog fur, like coming down from a maple. Sometimes they've got like these like big burrs that get stuck in dog fur. And so you can see here, this is the non-sticky form. Non-sticky, and then you can see the little spikes in the sticky form. So sticky platelets have a tendency to, you'll never guess, stick together like this, where non-sticky platelets do not stick together. Okay, so we're going to go ahead and draw out a capillary that has a rupture in it so that we can diagram the stages of hemostasis. I'm going to be using this entire page. If you have different colored pens or pencils, this is a good time to use them. Let's diagram plasma. So I'm not including the red blood cells here, but obviously all the fluid that would be in here would be plasma. And then out here is going to be the interstitial fluid, and then of course there'll be other cells hanging out. Okay, and in the interstitial fluid underneath the lining is also going to be supportive collagen fibers. It makes part of what's called the basement membrane. So this ends up being kind of important. So there's these collagen fibers, and collagen is a rope-like protein. So this is a normal capillary. All right, first thing I'm going to do is I'm going to rupture part of it. So let's make a rupture. Some sort of trauma. It's a very small amount of trauma, but it gives us the idea. So here's our rupture. Kind of explodes. Just trauma. Okay. And of course we expect blood to start pulling out, right? There's our trauma. Okay, so we also have platelets. So there's my inactive platelets that are running around, and they would be running around here too. those platelets are going to see the collagen, and that is going to activate them. So bumping into collagen actually activates the platelets. And that's going to make it sticky. That activated platelet is not only sticky, but it also secretes a chemical called platelet activating factor. Go figure. So now it's going to secrete this chemical that is actually a paracrine. And you know what that platelet activating factor is going to do? It's going to activate nearby platelets. So platelet activating factor is abbreviated PAF. And so that platelet activating factor is going to start turning any nearby platelet into an active form. And so what we expect then is that after, not even maybe a couple seconds, we expect these platelets to bind to the collagen. So they're actually kind of sticky to the collagen that's sitting here. And we expect these platelets to form a loose aggregation where they're stuck to each other and stuck to the collagen. And that is called a platelet plug. So it's going to stop the bleeding, slow the bleeding, but not necessarily be a complete foolproof or watertight wall. So this is called a platelet plug. Okay, so the first thing that happens in a break is the formation of a platelet plug. I'm going to show you an image of that. You can go ahead and take a look at this for a moment. And this is more or less what I described. All right, sticky platelets like to stick to collagen, or they like to stick to other sticky platelets. So these platelets that are produced are very sticky. And we definitely want to make sure any activated platelets end up here in the platelet plug and not, let's say, like attached there. We don't want them attached to healthy cells. Why? Because then if they do, other platelets will stick to them and you'll get a mass of platelets on healthy cells, which would defeat the purpose and possibly obstruct blood. So it turns out that healthy cells, intact cells, like this one right here, secrete a gas actually that repels sticky platelets. And that gas is called nitric oxide. And the abbreviation for nitric oxide is NO. The healthy cell says, no, platelet, you cannot sit here. And so this platelet is coming by and it's repelled like a magnet. And then it finds an area it's not repelled and voila, sticks to the platelet plug. So in addition to the formation of the platelet plug and the basic steps there, you also need to know that healthy cells secrete nitric oxide. So NO, let me write this out for you, NO equals nitric oxide. It's a gas, actually. And nitric oxide prevents sticky platelets from sitting on healthy cells. So it's only secreted from healthy cells. So let me go ahead and highlight the cells that are secreting nitric oxide. These are all secreting nitric oxide. These are secreting nitric oxide. That's secreting nitric oxide. The only place where there would be a dearth of nitric oxide would be the damaged area. And of course, that's where a platelet is going to drift down into. Okay, a platelet plug is a literal stopgap measure. It will slow the flow of blood out through the injury, but it won't stop it. So here's what we're going to do. We're going to need to reinforce it with a thick fibrous rope. So that thick fibrous rope is known as fibrin. So don't draw this out yet, I'll draw it for you separately, but what we're going to want to do is basically kind of reinforce this with a very tight basket mesh weave of what is called fibrin. Then you have what you might know of as a scab. That is a clot. The formal name for a clot is a thrombus. So our next step is going to be to basically lay down fibrin mesh over this platelet plug to reinforce the platelet plug and produce a true clot. So coming back up here then, we could really call this first step the platelet plug formation. And now our next step is going to be to reinforce that platelet plug. And this process also gets a formal name. It's called coagulation. This is where we actually form our true clot. All right, well, how does that happen? How do we get to coagulation? Well, we get it through a cascade of events. And it turns out that there's actually two different processes that kind of all lead to the same end game. So let me talk about the end game first. Remember fibrinogen? Fibrinogen is kind of an elongated plasma protein that looks like this. Fibrinogen is dissolved in plasma and freely floats dissolved, meaning you don't see it, it doesn't come out of solution, it doesn't look like a big rope. Fibrinogen is the precursor to fibrin. An enzyme is going to basically snip off kind of the end pieces here on fibrinogen, and what that does is that creates a much thicker protein that comes out of solution. And when it comes out of solution, it's like, where do I want to sit? And guess what it's attracted to? Sticky platelets. So this is called fibrin. Now, we're going to see this theme a couple times here. Notice fibrin and fibrinogen look very similar. The suffix gen means to generate. So to generate, to create. Fibrinogen is the precursor to fibrin. When it's activated, it generates fibrin. So fibrinogen generates fibrin. So that's how you can remember those. So what enzyme catalyzes this reaction? Thrombin. Thrombin, thrombus, sound familiar? Okay, so the enzyme that's actually going to cut off the ends of fibrinogen here, and I'll go ahead and draw a line here, is called thrombin. So thrombin is going to change fibrinogen into fibrin. Is thrombin always there? Because if it is, we would always be cutting up fibrinogen and we would be making fibrin, and that would be bad, right? So thrombin actually is not usually in its active form. Typically, it's running around the bloodstream as a plasma protein in its inactive form. The inactive form is called prothrombin, not a term I'm going to test you on, but there's an inactive form. So something must activate thrombin, right? Okay, so something turns prothrombin into thrombin. So you can kind of see, if you work backwards, that there's probably some funky little cascade of events where A activates B and B activates C and C activates D, etc., until eventually prothrombin gets activated into thrombin, and then thrombin starts taking any fibrinogen it can have and basically chopping off the end, and then that fibrin that is created is going to start sitting down on that platelet plug, reinforcing it, and form a clot. So this represents the clot right here. That's the clot. The process of getting there is called coagulation. how does a platelet plug lead to coagulation? And it turns out the platelet plug actually activates coagulation from two different pathways. There's one that's called the intrinsic pathway and one that is called the extrinsic pathway. I don't expect you to know the difference. All I want you to know is that there's actually two different pathways that end up at the same spot to turn prothrombin into thrombin. So what are activating these pathways? A situation that activates one pathway is going to be the actual damage of the cell itself. When a vessel cell is damaged, it releases chemicals that by itself are going to activate one of the pathways. The other thing that activates a pathway is going to be stuff secreted by the platelets. So the platelet secretes not only the platelet activating factor, but also something that activates the coagulation cascade from a different starting point. Again, they both lead to the same end game. Now, the reason that I bring up that there's two ways, two roads to Rome, if you will, or two ways to get to thrombin, and then thrombin takes fibrinogen and makes fibrin, is that there are people that have a genetic anomaly, whereas one step in this cascade, let's just say it's this one, doesn't work. Now, these steps in these cascades have names, and it's like clotting factor 7, clotting factor 5, right? So they've got all these names, different things that are going on in this cascade. And somewhere in this cascade, something doesn't work. And when that happens, you have a disease. It's called hemophilia. So if you've ever heard of a hemophiliac, that is somebody who often needs transfusions of clotting factors, actually, to help them clot appropriately. Hemophiliacs can often still make a clot, not that they can't ever make a clot or they would die very early in age, but it takes them a lot longer because one of these proteins is defective, they lose one of their ways to thrombin and they have to rely only on the other way. The longer it takes to form a clot, the more blood you're going to lose. So, of course, hemophiliacs are in danger of a small injury becoming life-threatening when they lose blood. Okay, so what do you need to know out of here? You need to know that there are two different pathways. They're called intrinsic and extrinsic. I don't care that you know which one is which. One of them is started by the actual damage to the blood vessel wall. The other is caused by an active platelet secreting stuff, including a stimulus that starts the other pathway. They both end up in the same spot. Their end game is to activate thrombin. Thrombin is an enzyme that takes fibrinogen, which is a long structural protein that's dissolved in water, cuts it off, and that makes fibrin. Fibrin comes out of solution and basically reinforces the platelet plug to form a clot. So what we have discussed is just right here. So now let's talk about dissolving the clot, because you're going to eventually heal that tissue, repair that tissue. You don't want the clot to be there forever, just like a scab eventually comes off. Inside the body, we need the fibrin to basically be dissolved, and the clot needs to dissolve. So that process is called clot dissolution. So I'm going to put that over here on the right-hand side. All right, clot dissolution. There's an enzyme that cuts up fibrin, chops it up into tiny pieces so it eventually flakes off the clot. That enzyme is called plasmin. So plasmin is going to be an enzyme that is going to break up fibrin and dissolve the clot. So my end game is going to be to have fibrin be broken up by plasmin. So for clot dissolution, I want plasmin, which is an enzyme. I'll put a box over it. That takes my thick fibrin and cuts it up. So that's going to be an enzyme that does that. But the problem is that we really don't want that enzyme to start working immediately, because if it does, then your clot will form and then you'll just chop it up and then you'll start bleeding again because you have not repaired the tissue. So you have to give yourself some time to repair the tissue first. So plasmin has a delayed activation. And it turns out that the precursor to plasmin is going to be plasminogen. So plasminogen is the precursor to plasmin. And so again, I mentioned that O-gen. Plasminogen is, guess what, another plasma protein. And it's going to be turned into active plasmin. So plasminogen is inactive. Plasmin is active. So how does that work? First of all, plasminogen, which I'm going to use as a little blue dot right there, inactive, gets trapped. It actually gets trapped in the clot. And then enzymes slowly find it and transform it into plasmin. What kind of enzyme? The same thing that we saw before, just cascades. What activates that cascade? The same thing that started the clot. So the platelet plug formation, you have platelets, you have damaged endothelial lining. Both activate the coagulation cascade. But they also start a longer process that takes a lot longer to happen, that starts the clot dissolution cascade. The end game is that plasminogen that's hidden in the clot, because it gets trapped when the fibrin comes down, starts getting turned into plasmin. And then plasmin starts cutting up fibrin into small parts. And as a consequence, you end up with just pieces that end up moving around, and the tissue hopefully by that point has healed. So hemostasis has 3 parts: platelet plug formation, coagulation, and then clot dissolution. I also want to put in that usually when you get damage, there's kind of a reflexive vasoconstriction that happens. So upstream arterioles or arteries will automatically vasoconstrict so that you don't get so much blood flowing to that damaged area. So it's just kind of a natural response that will help you limit the blood loss. But again, the clot formation, platelet plug to coagulation, and then finally clot dissolution. Now coming back to that picture here, now we've added in the plasmin, breaking up fibrin fragments. I don't use this term, don't memorize it. So we actually just have one more thing to talk about, and that is blood thinners. Blood thinners. So what are some blood thinners? Well, we have a couple. We have aspirin, we have Coumadin. I'm sure there are many others, but those are the 2 that are coming to mind. What does that even mean? What's a blood thinner? Well, it's something you will undoubtedly be responsible for as part of a patient's care, is either maybe prescribing a blood thinner if you become a PA or an NP, or administering blood thinners. But what do they do? What's a blood thinner do? And when you think blood thinner, to me, I always thought it made your blood more watery, but it doesn't. To make your blood more watery, you would have to have fewer red blood cells. And that's not what happens. So what does happen? It turns out that blood thinners reduce the ability of your blood to form clots. How would they do that? By interfering with some part of this. So interfere with the platelet plug or interfere with the coagulation cascade. I do expect you to memorize these because they're not terribly complicated. Aspirin is going to interfere with the platelet plug formation. Coumadin is going to interfere with the coagulation cascade. So it kind of treats you a little bit like a hemophiliac. My grandmother was on Coumadin. She had congestive heart failure, and so she needed her blood not to have clots, because if you have too many of them, it makes it more difficult for your blood to move. increases resistance, and therefore your heart has to work harder. So my grandmother was on blood thinner or Coumadin, and they changed the formulation and they made triple doses for her, but she was still taking the same number of pills. So before, I don't remember what the doses were, but effectively she didn't realize that each pill now contained 3 times as much as it used to, so she continued to take the same number of pills, which effectively meant that she increased her dosage by 3-fold. And the way she found out that she did this is she was black and blue everywhere. She was absolutely covered in bruises. So somebody who's on a blood thinner, particularly when it's overdone, can be black and blue everywhere because you're constantly like causing trauma to your blood vessels with banging into stuff, sitting down, and we just don't see the outcome of that on the surface of our skin because typically the clots, or the damage is not great and the clots are right there. Of course, when we don't make a clot right away or the damage is too great, you have a bruise. So that's what a bruise is. On the surface, it would form a scab. But on the inside, if you have internal damage and bleeding out, that's a bruise. So Coumadin, if somebody's got too much Coumadin, you'll see them bruised everywhere. All right, so that concludes our lecture on basically blood clotting and hemostasis.